Hello, and during this session we're going to be going through the physical landscapes in the UK. That covers both rivers and coasts. I've also included that logo there just to remind you to play, pause, rewind this clip as appropriate to ensure that you get everything, as I will be going at quite a pace. Quick reminder then, so your geography paper is split into 3 papers. The first paper covers natural hazards, ecosystems, coasts and rivers. This is what I'll be going through today. The second paper covers urban world, economic world, resource management and energy. And then finally, that third paper we know includes the issue evaluation, which changes every year, and your 2 elements of fieldwork. But today I'll be going through the rivers and the coasts section. To start with then, looking at rivers in the UK, we first start with our long and cross profiles. Here is the cross profile of a river. A cross profile of a river we can see is where you would chop it in half as it goes along, and you can see in the upper course it is V-shaped, in the middle course it is U-shaped, and in the lower course it is very, very wide and deeper. Please be careful to make sure that you've got the valley and you've also got the channel. In the valley is V-shaped, but the channel is narrow. The valley is U-shaped, but the channel is slightly wider. The valley here is very, very wide and flat, but the channel is very, very wide and deep. The long profile shows you how the gradient changes. So you can see there in the upper course, the gradient is very, very steep. It is a little bit shallower in the middle course, and it is very, very flat in the lower course. You can also see on a long profile the distance from the mouth to the source. The source is the start of the river. Fluvial processes, something that you'll all be very, very familiar with. We have our 3 processes of erosion. Hydraulic action is the force of air and water into that crack. So if there was a crack there, the force of air and water into that crack there to widen it. The next one is abrasion, the sandpapering action of rocks against a riverbed or bank. And then finally, attrition is rocks colliding to become rounder and smoother. And these 3 processes of erosion are the exact same for coasts too. I've also added in for rivers here vertical erosion and lateral erosion. Vertical erosion is downwards erosion. So if you go back to that long profile, you can see there that in the upper course, the river profile is very, very steep, and that is going to experience downwards erosion. That is hydraulic action and abrasion happening in a downwards motion, whereas in the middle and lower course, it is going to be happening laterally, which is why we get those meanders and oxbow lakes in the middle and lower course. How is material transported? Through these 4 processes. Traction are large boulders rolled along the riverbed. Saltation is smaller pebbles bounced along the riverbed. Suspension is fine light material carried in the flow of river, and solution, even though you can see it there, it would be dissolved completely like salt. That is dissolved material carried along in the flow of a river too. Obviously, as erosion occurs, these larger rocks get eroded to be the saltation, they get eroded to be the suspension, and finally then completely dissolved as the solution. Rivers have drainage basins. You can see the drainage basin here is outlined by the watershed. The watershed is an imaginary line that separates one drainage basin from another. And all a drainage basin is an area of land that is drained by one particular river. If a rain droplet was to fall here, it would go along this river, down this tributary, join the main river and enter the sea or the river there. If a rain droplet fell there, it would eventually enter this river. Whereas if a raindrop fell there, that rain droplet would enter another separate drainage basin somewhere else. I imagine drainage basins a little bit like a bath. It is the area of water which is drained by one particular river. In this case, everything would be going to the plug. Starting with formations of waterfalls then, so these are features of erosion in the upper course. We know that first water flows over the hard rock, then the soft rock, and that creates a step in the riverbed. As water starts to flow down here then, there might be a small crack, and further hydraulic action is going to force its way into that crack, widening it and deepening it to create a plunge pool. We now have a plunge pool which is beginning to undercut this harder rock above. As the hard rock above is undercut, remember this water is flowing down, hydraulic action is spinning around here, as you will also have small rocks, so you'll also get that bit of abrasion, further undercutting it, creating this overhang of hard rock. Due to gravity, this overhang eventually will collapse into the plunge pool, so there'll be more rocks down here, and the process will repeat. Hydraulic action will come down here. Eventually, this will become undercut and the waterfall will retreat upstream, creating a gorge. In the middle course, you get meanders and oxbow lakes. So I'm going to sketch this one out and we're going to have a bird's eye view here, and this will be a cross-sectional view here. So all rivers first flow straight as so, and the cross-sectional view would look like that. There may, though, be a weakness in the riverbank, and due to the flow of water, hydraulic action is going to attack that crack. What that will do then is we will get a weakness, and you can see there, due to that crack being on the left-hand side, there is now a slight undercutting due to that hydraulic action. From a bird's eye view, that will begin to look ever so slightly like that. We now know that the fast flow of water is going to be on the outside and the slow flow of water will be the inside. From a bird's eye view, that would look like the fast flow is on the outside and the slow flow is on the inside. As hydraulic action takes place, this will continue to erode. This meander will now get bigger, as so. And from a cross-sectional view, you can really see that now starting to take place, and it is undercut completely. Due to that fast flow of water, if I dot that in, we know it's flowing fast on the outside. That's actually going to slingshot to the other side and create a subsequent meander. So our next view of that will be that the meanders now will form subsequently down the river and will also begin to deposit material on the inside of the meander. So we've got the fast flow here, we've got the slow flow here, and because it's flowing slowly, all the material will be deposited there, and this is what creates a slip off slope, whereas on the other side we have a river cliff. And you will get that slip off slope here, and that fast flow, this is the fast flow will be on the outside, slingshotting in, creating subsequent meanders. Eventually, we know the neck of land between two meanders may become narrower and break, forming an oxbow lake. As two meanders erode through, the neck of land between them will become disjointed. Material will be deposited here, creating an oxbow lake. You can see another diagram of a meander there if you wish to pause the clip. Your example of a river valley in the UK is the River Tees. In this instance, we have high force waterfall in the upper course. Notice that on the river you can see that meanders are occurring in the lower course. However, for the purpose of our learning, we will say that meanders form in the middle course of a river. How are floods caused? There's physical and human causes of river flooding. First of all, our physical causes are heavy rainfall, not normal rainfall. Normal rainfall doesn't cause floods. Heavy rainfall, saturated ground which has already absorbed a lot of water, steep valley sides. Imagine a V-shaped valley there. If the water hits the sides, it's going to go very quickly down into the town. Steep valley sides is another. And impermeable surfaces. Rocks can be naturally impermeable, meaning they will not absorb water and it will sit on the surface and flood. Our two human causes are deforestation, because if we chop down trees, trees do two things. They absorb water, but they also intercept rainfall. Water sits on tree leaves, and if there are no trees, the water cannot sit on the leaves. For example, those trees there, the water will be sat on there. And if there's loads and loads and loads of trees, they will hold quite a substantial amount of water. But without them, they won't be able to do so. And building urban areas, such as tarmacking, concreting, which will increase surface runoff as it can't be washed away. A flood hydrograph then. A flood hydrograph shows you how a river might flood. And the orange section here, we can see the rainfall. So at just after 12 p.m, the rainfall began. You can see actually where the rainfall was really, really heavy and then it stopped. So the rainfall there was happening probably about about 6 hours that rain was falling for. But the river at this point doesn't flood. Obviously the river doesn't flood there because every single rainfall droplet doesn't fall directly into the river, it falls around the river, so it takes a while to fill up. And this is what you can see here, the rising limb. This rising limb is the river filling up in capacity. Notice at this point, the rain's actually stopped, but the water is still entering due to surface runoff. The rising limb is increasing before we get to peak discharge. That is the most full the river can be. And the time between peak rainfall and peak discharge is called the lag time. And that's really, really important because if the lag time is quite short, that means that people do not have time to prepare for the flood. But if the lag time is long, we can tell people there's been a lot of rainfall, the likelihood is going to be a flood, you can now evacuate. So we like long lag times, we don't like short lag times. And eventually, because the rain stopped over 8 hours ago, the river will now start to go back to its normal base flow, and that is called the falling limb. We can compare two hydrographs here. This hydrograph, hydrograph A, is how we call peaky, or sometimes flashy. Whereas hydrograph B, you can see, has increased at a much slower rate and then started to decrease. The likelihood is that hydrograph A is from an urban area. The land surrounding that river there will probably have concrete surfaces, so the water has rapidly run in, making this rising limb shoot up very quickly and then decrease. Whereas at B, it's probably surrounded by a field. The field has probably absorbed some of the water, which means the river hasn't filled up straight away. Only when the ground has become saturated, it fills up. Then it starts to decrease. Your example of a river flooding in the UK was in Boscastle in 2004. Hard engineering strategies we can put in place to stop rivers from flooding include river straightening, because if there's a river meandering like this, if we cut out that meander and make it straight, the water will flow much quicker away, therefore not flooding the land either side. We can build a dam like this to hold back the water, so if there has been a lot of rainfall, it doesn't come flooding down. And finally, flood relief channels. We can also put soft engineering in place. Afforestation, flood warnings. A flood warning is this: it is going to flood, leave the area. That might come out on a radio or a TV program. And finally, floodplain zoning that you can see on the right hand side here. Floodplain zoning says, don't build on there, but you can have a car park. Or if you are going to build on here, make sure your houses are on stilts. It is only the expensive buildings, you can see there, further away from the river, that are designated to be built there. Now we move on to coasts. As previously explained, coasts also erode in a similar way to rivers. Through hydraulic action, the force of air and water into cracks to widen them, abrasion, that's sandpaper in action against the riverbed, in this case the coastal cliff, and attrition, rocks colliding to become rounder and smoother. And this coastline here you can see has been very soft. This is actually made of boulder clay and it is eroding at an alarmingly quick rate. Looking at landforms of erosion on a discordant coastline, we get headlands and bays. Imagine a huge wave came into this location. That huge wave is going to erode that soft rock, in this case boulder clay, to create bays. That then would create beaches here and a headland sticking out, which would be made of limestone. At a concordant coastline, we get wave-cut platforms, where at high tide, hydraulic action will erode the base of a limestone cliff. That will create a wave-cut notch, and that land above will become unsupported, so therefore, due to gravity, will collapse. As the water retreats, that leaves this wave-cut platform, and the process will repeat. At high tide, hydraulic action will attack the base of the cliff, creating that wave-cut notch. The land becomes unsupported. Due to gravity, it collapses. The wave-cut platform then will extend and retreat. At a headland, sometimes you get a piece of land that sticks out and it will have a crack in it. Hydraulic action will force air and water into that crack, widening it to become a cave. As that cave is deepened, further hydraulic action and abrasion will be happening on both sides of the headland, and that cave will break through to form an arch. That sea arch then will be eroded from the base, but then also due to biological weathering at the top of the arch will become unsupported and again due to gravity collapse. That will leave a stack left over, which through erosion will eventually fall over and become a stump. There is another diagram there of a cave, arch, stack and stump for you to pause the clip and have a quick look at. Longshore drift. Longshore drift is how material is transported along the coastline. You first have a shoreline, and the shoreline separates the land from the sea or the ocean. And we want to focus on one particle of sand. Due to the prevailing wind, which in this instance is coming at a 45-degree angle, the prevailing wind will push the swash up the beach at a 45-degree angle. Now it might be 46, it might be 22, but we will always say it's at a 45-degree angle. The backwash then comes back down the beach, and the backwash comes down the beach because gravity is pulling it down. The prevailing wind will then push the swash back up the beach and the backwash back down. Swash up the beach at a 45-degree angle, backwash down the beach at a 90-degree. And this process continues, moving material along the beach. So that piece of sediment will go from there to there to there, moving along the beach. There's another diagram of longshore drift there if you wish to pause and have a look. The formation of a spit. After longshore drift has happened, remember you've got the land, you have the sea, then at the end of a beach there may be a river estuary. Sediment will be transported along the river through that swash and backwash motion. Swash, backwash, swash, backwash, swash, backwash. It doesn't just stop there at the end of a beach. It actually continues. But when it continues, that piece of sediment which first started here, then here, then here, will actually be deposited between the land and the river mouth. And that material will continue to be deposited as longshore drift continues. And you get this finger of land that extends into the river estuary, which we call a spit. That finger of land will start to curve. It starts to curve due to a secondary prevailing wind, which will make that begin to curve, and behind that spit then you will get a salt marsh and mud flats. There is a diagram of a spit there if you wish to pause it and have a look. Coastlines can be protected again by hard and soft engineering, similar to rivers. However, these methods, this one is called a groin. Groins are wooden or rock structures built perpendicular to the beach, preventing longshore drift. So then when the waves come in, notice that the waves will crash onto the beach rather than the cliff. The next one, this is a sea wall. Sea walls are made of concrete and they're often curved. What they do is they reflect the wave energy back into the sea, therefore protecting the cliff. They can be fantastic for tourists because tourists can walk along the top, however they do look ugly. This one down here is called rock armour. Some of you might call it riprap, which is absolutely fine. They are large granite boulders which absorb wave energy, therefore protecting the cliff. And you know it's protected here because that house has remained there. People who fish like this, because they can stand on there and they can fish off the riprap. However, they can reduce access to the beach, which is what we don't like. These are gabions. Gabions are the cheapest method of hard engineering, despite still being more expensive than soft engineering. They are metal cages filled with rocks, and what they do is dissipate the wave energy. They are very cheap. They can be easily installed by both you and me. However, if the waves are very, very dangerous, they can actually break the metal cages, and that can then cause harm to tourists walking along the beach, as it is a hazard. Our soft engineering strategies include beach nourishment or beach replenishment. What that is taking sand from the seabed or further down the beach and replacing it onto the beach, and also beach reprofiling. And these two often work hand in hand. The sand will be replaced on the beach, and then bulldozers such as this will spread the sand evenly over the beach, meaning that when the waves crash in, the waves are crashing onto the beach and not the cliff face. These two work hand in hand, as I said before, and tourists like this a lot because it provides a beach for them to use. However, the negative, despite it being cheap, you have to constantly replenish it every 10 years or so, which can be expensive in the future. Similar to Boscastle, which was your river that flooded, a village where a river flooded, you also need to know an instance which is being managed by Coastal Management Scheme. And our coast is the Holderness Coast, which extends from Flamborough Head down to Spurn Head. And on this map, you can actually see villages that used to exist, those lost settlements, those red dots. However, if you went to the coast today, you'd end up in places like Mappleton, in Hornsea, in Bridlington. You would be stood at the coast on those locations, but hundreds of years ago, you wouldn't be. Hundreds of years ago, there were further villages out to sea which have been lost due to erosion. So what they're doing is they are putting hard and soft engineering in place all the way along this coast. For example, at Bridlington, there is a sea wall. At Hornsea, there are loads of groins. But also at Mappleton, there are also groins that look like this. And the groins stick out to prevent longshore drift, so that sand doesn't move further south. However, that has caused conflict because they can't just build a sea wall all the way around the UK. That would be far too expensive. And there's a place further south of Mappleton called Aldborough. I'll write this out here, Aldborough. Aldborough is just south of Mappleton. And Aldborough aren't very happy about that groin there being built, because what groins do is they actually intensify the rate of erosion further south. Why does that happen? We're not quite sure. But when the waves come in, rather than attacking Mappleton now, they are refracted south and will attack Aldborough. And that is increasing the rate at which Aldborough is eroding. We call this terminal groin effect, and that is causing conflict along the Holderness coastline because some people want it protected, but some people cannot afford it. And that is then the deliberation, do you build groins or don't you?